What's going on? Coach Daab here with Daab Labs. This is the part one of my trigonometry remediation and foundational video. All right, so trig is a huge portion of AP Physics. You will not be good at AP Physics unless you have a good understanding of trig. Luckily, it's not super advanced. You don't have to do anything too crazy, law of sines, cosines, all that nonsense. But we do need to understand the right triangle and how it fits and what we can do with it, okay? So first, before we get into that, let's just uh, envision for a second. Let's say that I told you guys you could only give me directions either in up, one at a time, either up, down, or left, right. But you couldn't give me them both at one time. And let's say you wanted me to end up at some diagonal point, right? Well, the only way you would be able to explain that to me is by telling me to do some combination of upwards and rightwards or downwards and leftwards or whatever you're trying to accomplish. Okay, so I need you guys to understand that when it comes to vectors in physics, which are all of those things that have that displacement, or excuse me, that magnitude and direction, right? But every vector in physics is going to be every vector in our physics, AP1, is going to be some variation of x and y components, right? It's two-dimensional physics. Luckily for you, we're not doing three-dimensional physics, but it doesn't get that much more complicated with three-dimensional, right? You just have a third vector in the z-axis, right? So if you could do two-dimensional, you could extend to three, right? But point being here that two-dimensional, every vector that you see in physics is going to be either all x, all y, or a little bit of x and a little bit of y, right? So it's important for us to understand that any vector given to us could be split into x and y pieces, right? But first we'll start with this whole 5 up plus 3 over, right? We'll learn once we get to the actual vectors portion, right, that we'll talk about tip to tail method. But for now, let's just go ahead. I'm going to do the tip to tail here just because. And we're going to undo this guy. Oh, got a little bit. There we go. All right. So what's happened is I've taken these two vectors, that 5 up and that 3 rightwards, and I've put them together. And that result, right, or what we will call the resultant vector, is the distance or my straight line shot between start and finish, right? Okay. So this we call that big resultant vector. It is the resultant vector of me adding 5 up and 3 over, right? And if we wanted to find out what the actual mathematical value of this r, or resultant vector, between the two vectors added together, right, it would just be my good old-fashioned a squared plus b squared equals c squared, right, with c being our r here. And we could solve, right? So we'd have 9 plus 25, take the root of 34, and that would roughly give us that value, okay? But the important thing is understanding that everything is comprised of a combination, or one or the other, of these things here, right? Right in here, right? It's always going to be some combination of up or down with some combination of left or over, okay? And so that being said, when you're given right now, I'm sure you're like, oh, come on, dude. Like, at least pretend like I'm in high school and that I know what's going on. Like you're treating me like my child, right? But the problem is, once we go to something with a vector and expect you to make these connections, all of a sudden the wheels fall off, right? So this top part I just did, hey, let's add 5 up plus 3 over, and it gives us this r value. Yes, I could do Pythagorean theorem and I could find out what that value would be. Easy peasy, right? But then what happens when later on in your physics class you're given something? It doesn't really matter. Let's just call this a force vector here, okay? So let's just say that we've got some force, right, that's being applied like this, all right? What we need to understand in physics, right, this isn't, I'm not giving y'all the secret to all of math, right? This is specifically to help you in physics, okay? So don't, go off on a tangent about math convention, right? That's not my goal here. My goal here is for you to be successful at physics, okay? And so I say that because we're going to take this F and we're going to know that in physics, in our physics class specifically, this will always be, right? The max case in the X would be if F was all horizontal, right? So if the whole F was just some straight line, right? Like this. Okay. And then the other case, max case, would be like, what if this force was just all upwards, right? This force could be applied all upwards, and same deal here, right? This whole force is just going to be applied upwards, right? That's max case there, 90 degrees up. So our max x case is, right, let's go ahead and write this so y'all can remember this here. But our max, and I know this is pretty simple, but once again, very important, right? My max case in the x, right, is 0 degrees, right? Would mean if this whole force was just, boom, all at 0 degrees horizontally, all of the force would be horizontal, none would be vertical, and therefore 0 degrees, right? I don't know why this just happened. Okay, and so then let's look at our max case in the y, right? Well, this would be as if this force was 100% straight up, right? So that would be like if we did something like, sometimes it doesn't like me when I do the dashes, but you get the idea. But if the force was all upwards, right, then that would be 90 degrees, which would be the max case for the, so you can't see my little shapes here. But that would be my max case for the y, meaning if all of the force is applied at 90 degrees, it's all in the y. If all of the force is applied at 0 degrees, then it's all in the x. Those are our two one-dimensional conditions, okay? However, right, in most of the problems in physics, we start to very quickly get away from one or the other and get into some combination of both, okay? And so this is where it's very important when you see vectors, whether it's upwards like this, downwards, diagonal, doesn't matter which direction. The whole idea is that a vector can always be split into two components, okay? So when we're given a vector, like in this thing, blue vector here, the force, right? That vector can and will be split up into two components, right? And so let's just draw my horizontal components here. Okay, and I know it's not perfectly straight, but just bear with me. Assume that it's straight, right? And then we've got this here. And once again, I know it's not a perfect 90-degree triangle. Please don't kill me, right? But you can see what's happening here is we're taking this vector and we've now split it. It has two pieces. It has one piece that we would call the force that's being distributed in the x direction. And we have another piece that we would call what the force is exerting in the y direction. And then we have the combined, x and y acting together, which forms this resultant, okay? Resultant vector. It's a total vector that's comprised of those components, right? The important part is, I'm almost done here, bear with me. The important part is that this shape, this right triangle, will come up everywhere in AP Physics. Every unit, you name it, it's there, right? And there's a couple tricks we want to take away from this pretty basic set, right? First thing is that this interior angle is what we're going to call theta, right? We could talk about the other angles, right? But let's call this one phi. And then, of course, we've got our right angle here, okay? So we've got three angles in our vector triangle, right? Any resultant vector can be broken up into two pieces. And that vector will be a right triangle, or those two pieces will be broken up, right, in a right triangle with two angles and my right angle, okay? So now I want us to real quickly just do a refresher of sine, cosine, tangent. The whole point is not to do a bunch of trig, but to refresh, okay? So sine of theta, which is this one, right, is going to be equal to, remember this is our SOHCAHTOA, opposite, right, over hypotenuse, okay? So for now, I'm actually just going to put opposite over hypotenuse, okay? And then we know that cosine then, not con, but cosine then of theta should be our adjacent, right, over the hypotenuse. And then lastly, tangent is our opposite over adjacent, okay? We want to know this, but just so you know, this stuff is on your, if you don't know this, you're probably in trouble, but it is on your equation sheet, so it's not like you have to memorize it, but you should, okay? So those are our three sine, cosine, tangent, right? And so this is where I would you can kind of set this up however you want, but let's see here. I'm just going to let's call this x, y, and r. Okay, so I'm just relabeling these sides. The x component will just be x, the y component will just be y, and the total resultant would be r. Okay, so now I'm going to rewrite my equations that I did before, but with these new variables, right? So we have sine theta is equal to y over x. And then we have cosine theta is equal to x over, oh, I just realized that I goofed, not all perfect here. Let's see here. I don't know why I said y over x, it should be y over r. Hopefully you caught that, right? Cosine would be our x over r, and tangent would be our y over x, okay? So these, I'm showing you guys this A so you can kind of see how it all manipulates, but B, I'm leading up to this major trick in physics, which we very rarely use kind of this kind of convention. I mean, we do use this convention, but we kind of do a different format, okay? Because what happens a lot of the times, think about this. If you were, measuring something in the wild, firing a rocket, let's say I'm trying to take out New Zealand with an intercontinental ballistic missile, right? I usually have the resultant data, right? I usually can measure the resultant data just by tracking something's position over time. It's usually a little bit harder, not impossible, right? But a little bit harder to get individual X and Y components. So I'm telling you this because most of the time you'll have the resultant. Not always, right? In physics, anything can happen, right? But most of the time you'll have R, and you'll be looking for either X or Y, right? Usually, not always, but usually, okay? And so you'll see in physics, we kind of adopt this trick, this a little easier when it comes to solving for these unknowns by just go ahead and rearranging the equation so that the hypotenuse is not in the denominator, right, for sine or cosine. And so what do I mean by that is sine, right, this one becomes r sine theta equals y. Right, this one would become r cosine theta equals x. Right, and then lastly, it's a little bit different here, right? But x tan theta equals y. Right, these right here are going to be used, I'd say, 8 out of 10 times, and then another variation might come up a little bit, in some of the more rare circumstances. But point being, you usually have the hypotenuse, and a lot of times you'll have the angle. And so once you know how to write it like this down here, you're quite simply just multiplying the resultant times sine theta for that opposite, or height, right? Could be considered height. This could be distance or length, right? But the point being, this is the best convention for trying to solve for unknowns in a right triangle. And remember that right triangle is coming about because we're taking a vector, which is a two-dimensional vector that contains distance or is magnitudes in both the x and y. We have this resultant vector, right, that's representing those two x and y components. And then this right triangle helps us to figure out unknowns about that situation, right? And remember that I could give you a string with tension at an angle. I could fire a missile with some force at an angle. I could just have some speed at an angle, right? I could just have some momentum at an angle, right? My whole point being all of these are vectors, right? And so every single one of these can be broken up into its individual components using trig. In fact, we need to for most of our problems, okay? And understanding that the x and y act independently of one another. So the way you treat the individual motion in the x or the individual motion in y is it's happening whether or not that motion in the other direction is occurring or not, which I know sounds kind of weird, but once you really understand that concept, I think it makes things a lot easier, right? And when we start talking about how gravity is always acting downward but not horizontally, it starts to really unlock a lot of the keys to a lot of the secrets there. But I think this has gone on long enough about my trig. I just wanted to give you guys an intro, just to recap. We talked about how taking two one-dimensional vectors and adding them together would give us a resultant two-dimensional vector. And because of that, we're able to use trig, or our right triangle math, right, to solve for unknowns based on certain givens, okay? And then lastly, I showed you this trick for rearranging the sine cosine equations for a faster way to solve for your unknown. And then, as always, never forget whenever solving for an unknown side of a right triangle, as long as we have two sides, right, we can do our Pythagorean theorem. So hopefully this helps. There will be more trig supplement and other foundational skills videos coming soon. Until next time, hope you learned something.